I would like to spend the next 3 videos discussing some of the more theoretical aspects which govern some of the conclusions that we came to over the last couple of videos and will be important in understanding those to come. I want to start off by discussing thrust. And I'll use a rocket engine as a simple example because it's the easiest one to understand. The thrust given by any engine is governed by Newton's second law, F equals ma. Acceleration is the change of velocity divided by the change of time over which it happens. A is equal to delta v divided by delta t. Or if we were just to consider the acceleration at any particular instant where delta becomes very small, this can be written as A is equal to dv by dt. So we can rewrite F equals ma as F equals m times dv by dt. And this is fine for simple systems like a ball rolling along a tabletop, for example, where the mass is constant and the velocity might change. But in a fluid system, the velocity is often constant, and it's a mass which is flowing through as the fluid flows through the system. So it's more convenient to rewrite this equation as F equals dm by dt times v, where dm by dt is a rate of flow of fluid in kilograms per second, which is often called the mass flow rate and denoted by the symbol m with a dot over it. We can therefore write the thrust of a rocket as F equals m dot v, where v is the exit velocity of the gas coming out of the nozzle and m is the flow rate in kilograms per second of the hot gas. If a gas is emerging at a different pressure to the ambient pressure around it, there's also a force which is caused by this change in pressure. Force is equal to area times pressure, or pressure is equal to force over area. And so we can add on to this if the pressures are different. F is equal to A times P1 minus P0, where P1 is the exit pressure of the nozzle and P0 is the ambient pressure around it. Things are somewhat different in the case of a jet engine because there's air coming into the intake. And so we need to subtract the air coming in from that leaving. And so we can alter the equation which we developed above for a jet engine by saying that it is the mass flow rate out of the engine times its exit velocity minus the mass flow rate coming into the engine and the velocity at the intake. And we can further elaborate on this if we want to add in the flow rate of the fuel, if that has a significant effect. We can also add the pressures in, as we did earlier for the rocket engine, if we wanted to. However, often some of these terms are insignificant,